Mammals. They're pretty neat. Some of us may think mammals aren't exciting, and those people are what I like to call wrong. Mammals are amazing. Are you telling me that this isn't awesome? Or this? Or this? Come on, you know mammals are cool, you know it. But one thing they are not is colorful. The vast majority of mammals don't represent most of the rainbow, mostly being on the scale of black to white or representing shades of brown, to the point you'd think we're all a bunch of Xbox 360 characters. This wouldn't be so weird if pretty much every other type of animal didn't buck this trend and show a huge variety of shades and patterns. Sponges, jellyfish, arthropods, mollusks, fish, amphibians, birds, reptiles, even plants get in on the fun. You don't have eyes! Animal kind is a kaleidoscope of color. Why are mammals the exception? But before we answer that question, we have to ask this question. What is color? We see light as a given color when all or most of the light from something we see has close to the same wavelength, with white being a jumble of all colors and black being none of them. In nature, there are two approaches living things use to achieve these colors. The first being pigment-based color, which is just having a lot of a chemical of a certain color in you. Think about food dye. It's basically just that. How that works is a lecture all on its own about the shape of molecules and electron energy levels and valence shells, and I am already getting a headache, and it deserves a video on its own. So let's just take it for now. Sometimes stuff is a certain color, and animals have a lot of that stuff in them. The other is structural coloration, where various teeny tiny structures in an animal's body change which wavelength of light goes where, be it by refraction or by regular repeating structures. Only certain wavelengths of light can be reflected outwards. Like the pigment thing, the way this works is a whole-ass lecture on refraction angles and interference mechanics, so just take it as tiny geometry on the surface, make things be color. Got it? Baller. Moving on. A lot of creatures use both of these. You have cephalopods with exposable layers of colored cells to do crazy stuff, and bird feathers speak for themselves. Even creatures with no color adaptations that aren't trying to do anything special usually have something in their bodies that just has a color inherently, even if it's just something like blood. So to be as clear as glass is actually very hard to do from an evolutionary standpoint. That's not really relevant to this discussion, I just wanted to mention that. So where does this leave us? What, I ask you, separates mammals from sponges and jellyfish and arthropods and mollusks and fish and amphibians and reptiles and birds? Okay, yes, mammary glands, which literally define us and give mammals our name. But we're not talking about that today. I present to you hair. While there are non-mammals that have hair and bristles, nothing out-hairs mammals. Now, how does hair make mammals less colorful? Hair seems to be the part of the body most prone to color mutations, and it's quite similar to birds' feathers, which are magnificent. The truth is, hair, while similar to a bird's feathers, is fundamentally different. Feathers are a highly adapted covering with complex structures to help them hold their shape, which allows, in addition to impressive shapes and flying, amazing color through structural coloration, even to the point of iridescence. Metallic, reflective, amazing. Mammalian hair, meanwhile, is a very simple structure. Compared to avian feathers with their gewgaws and their doodads, our hair is basically just a solid rod of keratin. We can't have structural coloration because we just don't have the equipment to develop it, and it would take millions of years of evolution to develop even the baseline traits to then develop structural coloration we really don't need. Unless you're a polar bear, apparently, which they don't have white hair, they have clear, hollow hair that scatters light and makes them look white. Coincidentally, the same way as the snow that they live in. Neat. Even if we were to lose most to all of our hair and leave our skin exposed, like many creatures do, our skin is simply too soft, too squishy for that kind of thing. So, what about pigment? Pigment makes things more complicated because it doesn't matter how squishy you are, you can still have pigments in your skin. It doesn't matter if your hair is amorphous, you can have pigments in them. So what's up with that? What is that? What's going on with that? Well, dinosaurs. A very important part of mammal history is that we spent the first large chunk of it coexisting with the dinosaurs. And I'm not gonna sugarcoat it, dinosaurs were definitely the dominant group when we overlapped, so much so that mammals were largely forced into nocturnal lifestyles to avoid them when the dinosaurs were active during the day, which is something we still see in this modern day in some animals. Lemurs are nocturnal when they overlap with simians, where only on Madagascar are lemurs active during the day when there are no monkeys or apes. Other than, well, you know what I mean. Mammals showed up in the Middle Jurassic, so much like the mental scars incurred by attending middle school, spending the first 2/3 of their existence as nocturnal underdogs had some substantial long-term effects that still stick with mammals to this day. Some of these traits are good, like our aforementioned fur and excellent ability to maintain a constant body temperature from being active during cold nights. The most important trait is our lack of color vision. If you are active at night, there's not much color to be seen, so you are not going to spend energy on color receptors you won't use. And to this day, most mammals only have 2 color receptors compared to the 4 receptors most birds, reptiles, and most things have. Since being colorful is most often used for communication, if your fellows can't see your snazzy new coat of paint, chances are you won't get one. Even outside of intraspecies communication, having spent the majority of our history being active in the dark, there'd be no reason to evolve traits for vibrant color when nobody else would see it either. And once genes are gone, it's hard to get them back. But you know what's not hard? Subscribing to my YouTube channel. Got him. Simian primates are among the few mammal groups to have regained color vision, which goes hand in hand with, well, primates are pretty colorful for mammals. Golden snub-nosed monkeys have blue skin, and that's nothing compared to the spectacle of mandrills who are covered in vibrant blues and reds, and of course the most colorful primate of them all, us. Yeah, I mean, we're not naturally that vibrant, but come on, it counts. All in all, I think this just really illustrates why mammals are the best. Keep us down for 140 million years, we're just gonna use what we got to get better at living in cold climates. Our natural covering is primitive and can't do colors? Screw you, we're gonna have fun patterns anyway. Lost our color vision? How about we re-evolve it, and then cause a mass extinction? The more you look at mammals, the more it's apparent we're just flying by the seat of our evolutionary pants. In every elephant, in every big cat, there's still a grain of that frightened, Cretaceous little multi-tuberculate weirdo. Never forget what you are, mammals. I sure won't.